Hey, welcome and hello. It is June 24th, 2020 at 9:48 p.m. We got a little bit of a late start. My bad. Okay, I actually thought that it was going to get darker sooner. My mistake. It didn't. So we're starting now. But guess what? The gang's all here. Ta-da-da. I have Amanda here with me. Hello, Amanda.
Hi, Mark. How are you?
Awesome. And guess who else
Hi,
is
Jack.
here? Daryl is here. Hey, Daryl, what's up?
Hi, Mark. Hi, Amanda. Hello, everybody.
Yeah, Daryl is with us. Amanda's with us. I'm the only
Mark's
one.
with us.
I'm the only one that's not here.
Yeah.
I'm out in the universe. Oh yeah. So I just
As
got
long
in.
as the clouds aren't with us.
No, so far they're not, and I like that. This is the star Vega that's actually in our view right here. I like Vega. You know, it's really nice and blue. You know, it looks so pretty. Yay! Oh, it's a little hot. But Vega is really kind of an important star because it sort of comes up before Deneb and Cygnus, and then Altair, which is further east. And those three stars, Vega, okay, Deneb, which is down there, and Altair, which is down there, form, not in the view, but in the sky, they form the summer triangle, and Vega's the first one in the northern hemisphere anyway that'll come up to actually make itself known. So when I see Vega, I know that the summertime sky is on its way, and you know from a couple weeks ago that we did that amazing stream where we had a night, it was 5 hours long, and I just couldn't stop taking pictures. I just couldn't, you know. So it was a beautiful night, and Vega's the herald of summer, so I think I'm going to like that very much. So that all said, tonight we're going to do a few things. We're going to be looking at some nebulae that I know about. We're also going to be hearing from Daryl, who's going to talk about some objects in the sky that we need to pay attention to. And I mean, you better pay attention to these. I'm just kidding. And then if Amanda has anything she'd like to offer up, I'll turn it over to Amanda as well. So that's.
Don't hold your breath on that one, but thank you.
Well, yeah, okay, whatever. You know, you know more than you think you know, as you've proven time and again. So it's okay. You know. Okay, so that said, I'll bring down the volume here of the music because I want to make sure that we are still over it. I want to say hello to everybody. Hey, Dagger. Hey, Tina. Peterbar's here. Amanda's here. And then, okay, I don't know how to say that. Is that something Joe? Is that Randy Joe or Brandy Joe? Okay. Yeah, see, I think I figured it out with the symbols. That's pretty cool. Is here. Ronald is here. And naturally, Daryl's here. Genghis is here. And Marianne Robb is here. Hello, Marianne. And I want to just say hello to all of you. I want to say hi to Daisy and Zoe Amethyst who are here. I want to say hello to, to Johnny Unitas who's here. Johnny, welcome and congratulations with your new acquisition. you know, he's earned the wrench. And so that so far is, you know, who's here, and we have Cypher 2 here as well.
I think Cypher was the first one in here tonight, yeah?
He was, in fact, the first one in here. Yes, that's right. So I'm really looking forward to some nice sights tonight, and I'm glad that you guys are all here with me to see them, because we just love what we do. All right. So that said, let's go looking. All right. First up here on The Price is Right. We are at Vega right now, and Vega naturally is the herald of the Milky Way too. There's the Milky Way. Let me get the this guy out of the way here just for now. You can see the beautiful Milky Way over here, and when we look at the Milky Way, it really, and this is our view. Actually, this is the observatory, the remote observatory, and this is our sky. This is our actual sky. Not, you know, this is our actual landscape, I should say. There is the house. Anything toward that side, that's the west. If we don't see it by now, if we missed it by here, that means that we lost it all season long as it was coming up from the east. So that's why the observatory is where it is. We have Arcturus right here, and if we actually go and add some details in here, okay, we can actually look straight up and see what's overhead. You'll notice that we have some really cool objects right overhead, namely this one. This is the Great Star Cluster in Hercules, Messier 13. We've seen this before, and it probably will look beautiful tonight. Right now, I'm going to be checking out a few other things. I'm going to try and go to the Ring Nebula first, because we've done this before. I like the ring, and this will kind of give me an idea what the night looks like. You'll see the star zip away here as we start to move down toward the ring. And you'll see the telescope indicator moving to a particular star. This one is Sulafat. This star is in the constellation of Lyra. And what is Lyra? Well, Lyra is the lyre, the musical instrument, the lyre. And from Sulafat, which is right there being centered, we should end up going to the ring. Now, I've noticed, again, I've told you this before, there is a defect in the software that comes with the telescope, and if you tell it to go to Shiliak here and then go to the ring, it won't. It'll end up somewhere out here. But if you tell it to go to Sulafat first, or if it picks Sulafat first, then you'll go to the ring. So now now it's out here. So I'm not sure it actually went there yet. Let's just go take a picture to see. We'll just do a quick shot. I could be messed up here with my finding, and I'll just have to do it another way, which is easy enough to do.
Amanda, I'm not sure about that, but I want to say Orpheus. I could be wrong.
How did you know I was already in the background looking it up?
Oh.
I feel like it was an episode of Xena that I've seen a million times, and I should know this.
Yeah.
Who the lyre belonged to, Mark?
Oh, okay. I was wondering.
Orpheus is a good guess.
Yeah, see, this is the problem. I did not it's a beautiful starry field, but it's not the right starry field. So I'm going to bring us back and get this back in. I don't like how that does this sometimes. So first, let me just say, let's go to this star here. We'll go to this star. The Hipparchus catalog star 93017. Really not a big deal, okay? But we'll go there and we'll see if it's going to bring us to the star. If it brings us to that star, then from that star we'll jump to the Ring Nebula, and maybe it'll work. I can move the telescope too, and once I see where it's going and where it's placed in the field, so it'll help me figure it out. Okay, so and it centers. It's doing the high precision pointing right now, and then it should move over to that star. And there it is. It's moving to the star. So see? It knows what it's doing. And that's the star right there. Okay? Lucky us. So now, what we can do is, from there, we can just tell it to just zip on over to the Ring Nebula very quickly. Again, I'm fighting a defect in the software. So, that said, let me just do one thing first.
Amanda, I thought I was wrong once, but I was mistaken. That's a joke, okay?
It's a
Don't
good
take
joke.
that seriously.
No, I've used that once or twice. Yeah, I like that.
I said that during a presentation at work once, and people did not get it, and I got in trouble for it.
Really?
Yeah, it's a joke, people.
That's
And
funny.
hello, everybody who greeted me. I'm sorry if I didn't greet you by name. My typing is not optimal right now, so if I just say hi, I hope you'll forgive me. But Rockstar, Marianne, Do, Ronald, everybody else, hello, hello, hello.
Hey, Rock. Hey, Mary. I said hi to Marianne, of course. And Do, I didn't see you. I'm sorry for that, too.
Who has a burnt leg?
He has what?
A burnt leg.
Burnt leg. What happened? Muffler?
Yeah.
Oh, wow.
Carrying a generator with the muffler.
Oh,
Hot muffler.
that is painful. Those are painful. We were out in the desert, and we had a barbecue, and the guy lit the barbecue and didn't seem to light. And he kept trying to light it. Gas was on, gas was on, gas was on. And finally it lit, but from underneath the cabinet. And it blew the doors off of the cabinet and scorched his legs. So a nurse that was on hand and we put compresses and immediate cold water on it to pull out the latent heat from the burn, and got him off to the hospital. It was quite a time, let me tell you.
Was that man you?
No,
Okay.
it was not me.
I was just joking.
Yeah, no, it wasn't me. It was someone else, a good friend of mine. But all right, let me zip over here. That's a little too far. Yeah, no, it wasn't me. It was my friend Chuck, and it was a couple of years ago, actually. It was a couple of years ago. And here we go.
I don't know. When I hear, I don't know,
What?
explosions, things blowing up, I think maybe.
Oh, well, you know what? That's fair. Sorry.
Well, I mean,
It is fair.
telescopes crashing and blowing holes in your friend's garage door, and
Yeah.
you know,
Yeah, that wasn't.
I'm just teasing.
No, but that's very true, though. You're absolutely right. Okay, let's go see. Oh, I got it this time. So I just steered ourselves to it, and it's now here in the view. It's right here. You can't see it yet. You might be able to just barely see it, but I want to check out how it looks tonight. So we're gonna do 25 seconds at 3200. It'll be pretty bright. Actually, let me drop that down a bit. We'll go down to 2000. And this is the Ring Nebula. And we should have a guide star by now. So let's go. Yay. The Ring Nebula is a amazing nebula. These are planetary nebulae, so named because they look like planets through an eyepiece. And they really honestly don't look like planets. So I guess maybe with certain telescopes that don't show them with high enough resolution in the old days, then maybe this would be true. You know?
When I first started looking at the Dumbbell, not the ring in this case, but I remember distinctly thinking when I first saw the Dumbbell Nebula, it looked almost like a ghostly planet Earth.
Oh. Okay. Well, I would not call it a ghostly planet Earth, but I guess the Dumbbell has that look, doesn't it? You know?
Yeah, the what I call the apple core, you might construe as the continents, like North and South America on
Yep.
the globe of the Earth, and the fainter parts to the outside, like the oceans.
Yeah.
Just had sort of a look like that.
Sure. I mean, here we have the ring right here, and you can see, right there, you see that little tiny star in the center. That star is that 14.5 magnitude star that I think that's really, it's just, I call it a star, but it's really the stellar remnant. The former star has long since, dissipated much of its material in this outer ring here, and this is why it's called the Planetary Nebula, because it looks sort of like a planetary shape, okay, but you notice this stuff is out here. This is that ejected material that actually came, off the star and just sort of went and then got sloughed off the star as the star began to pulsate as it got older. It turned into a red giant, and it expanded and contracted and expanded. Some of the stuff went away, and then it contracted inside, and some of the stuff still going away, and it kept doing that. And so it made these shells of expanded material, and it's really interesting how planetaries like that form. And the Dumbbell Nebula is no different. The Dumbbell is a different type of what we call morphology, though. It looks like an hourglass in some ways. In other words, there's a concentration of material in the north, well, I won't say north and south, but the upper and lower parts of it. And those two lobes represent a bipolarity, where it's like most of the stuff is distributed along one axis and less on the outside axis. And we'll see that later. This is a rather nice night. We are shooting, by the way, in white light. We are not using any nebula filters right now. We're just using white light. I can use the nebula filters later. I just wanted to show you this right now. That said, let's go back to our view here. And I want to bring up our planetarium system here. And I want to see just how far... Yeah, I think that the dumbbell's going to be still pretty low in the sky, actually. I'm going to actually get... let's do this.
Not far from Alberio.
No, but Alberio is only about 27 degrees above the horizon. So it means that the dumbbell right here is literally going to be about 22 degrees above the horizon. So not much. We'll give it a little while. Meanwhile, I know we could look at M56, this beautiful globular. You want to look at that?
Sure.
Yeah, me too. So here we go. Boom, off we go into the wild black yonder. And it might use Alberio as our marking star, which it does. Look at Alberio. What a beautiful star. It's actually at 2 stars. These 2 stars are separated by over 5,000 astronomical units. Now, the distance from here to Neptune is 30 astronomical units, and Pluto is a little further than that. And it took 15 years for us to get to Pluto. Can you imagine going from one star to the other with our technology? 5,000 astronomical units, right? So it took 15 years roughly to get to Neptune, say 14 years, 13 years, and multiply that, or take 5,000 and divide it by 14, and that's how many years it would take to get there. So just one star to another, and they're both orbiting each other. Massive gravitational force between them. Okay, so this should be M56 somewhere in here, and let's go find out where. We'll do a 25-second exposure at 2500 this time, and we'll check it out and see what we have. I suspect that we will have M56 waiting for us, probably right around here. That's my guess. And we may have to rotate the image too, but we'll see. But here we go, any second now. Now, Messier 56 is really a beautiful globular. There it is, and I gotta just roll it to the right. There we are. Yeah, so you can see in our chart, in our Finder chart, by the way, let me move this over a little bit. In our planetarium chart here, you can see that Messier 56 is shown as a tiny little, it's a very, very small object in here because it's actually 33,000 light years away. You know, so that's actually pretty far away. So, and the globular clusters, they vary in sizes, but not by that much. And if they're closer to us, they'll look a little bigger. That's, you know, how they'll look. So here we have the globular cluster and Messier 56. It looks a little bit, you know, nice here. It's just a little. Again, we're in white light only. We're not using any filters yet. But you can see that this cluster is actually a little bit small. Low surface brightness, relatively. You know, hey James Dugan, how you doing? So I think that's pretty interesting. Incidentally,
Mark.
Yeah.
Excuse me. I'm sorry.
Go ahead.
Do you remember who was it who plotted all the globular clusters in the Milky Way? Besto Schleifer, somebody like that. You know, figured out they're in a halo around our galaxy.
Yeah, that's true. And I don't remember the name. Maybe it was Slipher. I'm not sure. That's
Shapley, Schleifer, someone like that.
Yeah, I'm not sure, but it's true. If you imagine our galaxy as, you know, a nucleus of stars with spiral arms coming out, it's more of an elongated nucleus because we're what's called a barred spiral. We have more of a bar in the middle, and the spiral arms come off those bars, okay? And that bar that's in the center of our galaxy and the spiral arms is not all there is to the galaxy. There's plenty of other material, matter, stars forming, and the spiral arms have lots of new star formation in them. But in a halo around the entire galaxy are globular clusters. And they orbit the galaxy. They go around the galaxy, and they go mostly any old direction. They're not going in any particular way. And they orbit down through the disk of the galaxy, and then they come back up through the disk of the galaxy. Some go on angles around the galaxy and other loops, but they're all orbiting the galaxy in a long, slow, lazy ellipse. They all have their own orbits. So it's really interesting what happens when these globular clusters go through the galaxy disk. Then one of the things that could happen, and this is speculation on my part, one of the things that could happen, and I think this does happen, is that they might shed stars and leave some of these stars behind as they go through. Or they might pick up stars as they go through. Remember, they're not just whipping through, you know, like a bullet through water. They're actually moving at a leisurely pace, and some of the stars are moving at a somewhat leisurely pace as well. So if it gets close enough, it might just, you know, capture a star as it goes through, and then that star may orbit the globular cluster, may fall into a stable orbit. But we're only seeing a snapshot in time. And for all we know, all these stars here that we see in this globular cluster could be in the process of being ejected because they were picked up the last time it went through the disk. Or they could be going into the globular cluster from the last time it went into the disk. So we don't know. And that's something that I think is a really fascinating line of research. One that I would actually like to pursue in general. But it's pretty cool. I think it's really interesting. Messier 56 is still kind of in the murk. It's only 30 degrees above the horizon, though, so you see, kind of looks a little fuzzy. You know, and the Ring Nebula will get better as well. But what I'll do is, what I want to do actually, I'm going to look at the blinking planetary right now. This is another planetary nebula, and we'll go check that out. But first, let me get us back to, let's set over there first. And now we come back here. You can see the stars zipping by, and we're going to a particular star to act as an intermediary. That star, of course, is one of the stars in Cygnus, and it's this star right here called Phawaris. There it is.
Hi, Tana.
Tana's here. Hey, hi, Tana. And hi, Tara. Tara's here as well. Tana and Tara. Amal, how you doing?
Amal?
Yeah, he's here.
Could you back out on the Cygnus there a little bit?
Sure.
The planetarium view?
Yeah.
Okay, when you see Cygnus there, people, that's the swan. The head is Alberio down at the bottom right. And Deneb is the tail. Deneb means the word tail. That's like the tail of Leo is Denebola. And then the wings on either side. But something that doesn't often get mentioned, or not lately anyway, there is an asterism, an unofficial star pattern within Cygnus called the Northern Cross. And for that, Alberio is the tail of the cross, and Deneb is the head. And the tips of the left and right tips of the cross are halfway out on each of the two wings of the swan. Do you see that?
Yeah.
So Deneb is the top of the cross, but it's the tail of the swan.
Yeah, and we call it the Northern Cross, just like Daryl said. There's a Southern Cross too, and it's called Crux, and it's in the constellation of Crux. I've only seen it once in my life.
Never seen it myself. I gather you can just see it from down in southern Florida.
That's where I was. I was in southern Florida, and really, it was quite beautiful.
Yeah.
It was rising out of the water, actually. It was coming out of the ocean, and it was just so stunning. I was down there, actually, to photograph Halley's Comet, and we had taken an airplane to a remote key where we set up our telescopes, and we took pictures of this thing, and then we saw this gorgeous, this absolutely stunning crux, Southern Cross starting to rise out of the water. I got a bunch of great pictures of it, and I wish I could actually find them. I have no idea where they are. Which is really terrible. Okay, so this is the blinking planetary now, and let me just grab that again. It's blinking so much I can't even see it now. Where'd it go? Oh, there it is.
It blinked.
It blinked, yeah. Okay, so let's just take a picture. This is probably it right there. I could be wrong though, but we're gonna do a shorter exposure here. Just gonna do 15-second shot to do a little finder shot for the blinking planetary in Cygnus. So let's check it out. Oh, can't miss it. Look at that.
Wow.
That has Amanda's color.
Sure does.
That is gorgeous.
Yeah. And I'm going to...
I love that.
We're going to take a few shots of it, Amanda, to get it a little sharper and clearer for you. Because I thought that was it. Okay, I'm going to drop down the ISO quite a bit, down to 1,000. Okay, and then we'll take a 10-second shot. We'll do 10 and 1,000. I want to try and get the some of the subtle detail in this planetary. Remember, a planetary is the remnant of a star that has ended its life. There we go. This is really pretty. When a star ends its life, it can go a number of ways. Okay, when we look at the Veil Nebula, okay, the Veil supernova remnant, it's not this. This is the remnant of a star that actually did what the Ring Nebula did. Okay, it expanded its shell. It had an expanding shell of gas that it just took right off the outside. Okay, as the star pulsated and puffed up, some of this material ended up becoming loose from the star. Basically, it was no longer gravitationally bound, and so that allowed the star to have this hazy gas around it. But the interior, that center part right there, that's actually a white dwarf deep inside there. And that white dwarf is very hot, upwards of 40 to 50,000 Kelvin. And what that does is that can ionize some of the atoms that are out in this gas cloud that are expanding away from the star. Ionization will cause these things to cause this gas to glow, causes these atoms to glow, primarily when the electrons that are ionized or knocked off the atom rejoin the atom. Okay, that causes these things to glow. The atoms will glow beautifully, and depending on what the atom is, if it's oxygen like this, then we will see this beautiful blue halo, all right, of blue oxygen 3, which is doubly ionized oxygen. All right, so this is just a gorgeous planetary, and it's actually if we put it in terms of its location in the sky, well, now you can see that. Okay, this is no. Okay, this let me do it again. Okay, this is the 1-to-1 size. So look how small it is. Okay, for us to see it, we have to zoom in quite a bit. You'll notice, though, very carefully, there's a subtle reddish hue around the outside, isn't there? See it? And there's blue. Well, this reddish hue can either be hydrogen gas or neon made in the star, or something that the star might have actually had with it that never was used in fusion, most likely, because the star that made this nebula that left behind this very, very hot white dwarf was a star kind of like the sun. And the sun isn't hot enough to make all these additional elements, in its atmosphere. It most likely can't make oxygen in the core. It can't make neon in the core. It might make carbon, but then you have nitrogen and oxygen after that, and fluorine and all that. So it may make carbon eventually, but that's about it. So that said, this is a beautiful nebula. This is showing very well tonight, Daryl.
Yeah, it looks like it's a little wider too, in the about 8 o'clock to 2 o'clock axis.
This way?
Yeah.
Yeah, I see that too. There might be, we might benefit from doing a longer exposure just to see what we get, shall we? Let's see if we get something that shows us a little bit more what's going on in there. And I'll leave us on the white light shot. I'll do a 25 seconds, but I'm gonna pump this up to twice this. I'll go to 2500. Actually, go to a little higher. Oops, that's too much. That's still too much. It's trying to go down. Okay, so 2500 and 25 seconds. Let's see what happens at that. So, the trip to Arizona, I just got back last night, yesterday, actually around midnight, and I got home, and when morning broke, I went out into the dome and I installed the circuit that's going to drive the telescope when it's out in Arizona. And the circuit to drive the telescope, that's pretty. The circuit to drive the telescope is actually something I had to write, because there's no circuit to go by. And this circuit was really, really nice, and so it does some really nice things, including it can prevent me, I should say, from doing stupid things like closing the roof when the telescope is still pointing up in the air. Can you say lop it off at the top? Well, we don't want to do that. So I have it set up so that if you try to close the roof, it'll say you can't do it until you park that telescope in its storage position. And then I have it set up so that you can open and close the cover using what's called a stepping motor. And tomorrow I'm going to design and 3D print the parts to actually go on the stepper motor that's going to allow it to open and close the arm which is going to hold the caps. Because we have several caps to take off the telescope because there's more than one telescope there. There's a guider telescope, and then there's the main scope. And the main scope has a gigantic, cover, and the smaller scopes have a small one like this and a tiny one like that. And so I have to figure out all that. I've got it all straightened out now. I know I have the distance that it has to go all figured out, and I just have to make the 3D printed arm, which I'm going to do on the 3D printer that's behind me, and then on the new 3D printer that I got, which is the SLA printer, that I'm going to print the actual hard mount that's going to mount this to the telescope, because this is a heavy motor and it's a very, very high torque motor. So I need something really strong, and this SLA resin is very strong, and I'm going to print it solid. What are you saying, Do? What do you mean?
Uh-oh.
What does that mean?
I think he's on to us.
Don't realize he's in trouble with the 3. What?
Oh, nothing. Keep talking.
Maybe I shouldn't.
Haha.
Well, I didn't figure it out. I missed something.
It's just our ongoing taser fantasy.
Damn it, Marianne, will you cut it out? You know what?
It wasn't her. I think we started it this time.
Yeah, well, you know what? I have a shotgun now. So there. And it's actually, it was a gift. And it's from someone in the chat. And I took a picture of it. It's actually being stored at the police station out there. And I went to the police station. Actually, I had to because I found some poor woman's credit card on the ground. And I picked it up carefully with a piece of paper in sterile manner, and delivered it to Marianne Robb, who was the police officer. And she said, all right, let's go down the station. And we went down there, and she said, by the way, your shotgun's here. And she showed me the shotgun. I got to hold it, and I was able to check it out. So it was a really nice little Mossberg 12 gauge. And I'm not a terribly big gun fan, especially a fan of the shotguns, because the last time I shot a 12 gauge, I thought my arm was gonna fall off.
Oh my god!
One shot, and it was just like the kick was like, ow.
You didn't have it tucked into your shoulder tight enough.
Well, you know what? That's what Marianne said, and she called me a name I won't say publicly. But you know what? I will probably get good at it, But I mean, out there, you've got to be careful. You can run into some creatures that want to make lunch of you, or just kill you to be, to have their way with you, like rattlesnakes. But you don't use a shotgun on a rattlesnake unless you want to shoot everything else around it too. But out there we have 9mm handguns that actually you fill them with snake shot. And think of it as a 9mm round, which has a little tiny set of BBs in the end instead of a bullet. And that snake shot just does wonders. The snake's head vaporizes. Now, I don't kill things. I'm not a killer of things. I'm not a hunter. I don't do that. So what's the point? Well, the point is, if I have no choice, I'd have to do it. Don't want to, but if I had no choice. Anyway. Yes?
Well, that's one of those things. It's better to have it and not need it than need it and not have it.
That's a very good point. Yeah. So, and Daryl, you speak the truth. But you know what? Marianne and her husband Don are avid hunters. And when you go in their house, you think you're going into a zoo. They have trophies everywhere, and I mean, but one thing they don't have is a rattlesnake all curled up, in that, looking, that pose. So I think she has to go and get a rattlesnake now, but she has to catch it by hand, you see, so that she doesn't destroy the snake. Okay, catch it by hand, Marianne, by hand. Okay, you can hypnotize it. Don't worry. I'll help you. Actually, you could probably tase it. You know, you could probably tase the snake. Never thought of that, but tasing it might work. Anyway, back to here.
Hold on, I'm hung up on the first thing you said about that. Did you say a listener sent this to you?
Someone in the chat gave me a shotgun. Yes.
Did you ask for one, or was this just a random present?
It was a present. Yes, a random present.
You didn't know it was coming?
I did not.
Wow.
I did not. Yep. So I thought that was very nice. And I'll leave it at that. And if that person wants to say that it was from them, then they can say so. Otherwise, I will let it remain anonymous. But it was really kind of nice, you know, considering that, you know, I'm planning on getting out there and moving out there. So I thought it was pretty nice. Nice thing. Anyway, you still hung up, or can we move on now, Amanda?
No. Ronald wants to know if there are any stars in the blue part.
Well, only one, Ronald, and in a sense, it's gonna be, you know, this guy right here, right? This is a white dwarf that's in here, Ronald, and this is the remnant of what was the star that made this, okay? And that's what we're looking at here. So it's only the remnant of that star. There's nothing else in there, and these planetary nebulae, they only get to a certain size. They only grow to about a light year across, because that's about the distance that the white dwarfs can typically ionize. So about a light year, you know, for these planetary nebulae. So there's a lot. There could be, and this is why we can't really get their distance too well, is because there could be gas far beyond the outsides of this nebula that we haven't mapped yet. And if there is, that means that the nebula is a lot bigger than we think. And if you only go to how far out the white dwarf can, you know, do this this ionization, you could say, well, it's approximately a light year, but it depends on a lot of things. Okay, it depends on what type of atoms are being ionized. It depends on what state they're in. It depends on many things. It depends on other interactions in the interstellar medium. Anytime you have gas out there, gas can be affected by a lot. You know, I want to say hi to Trish D. Hello, David Schmidt. Hello, and is here. How you doing? And Roxana.
She wants to know how nothing else can be in there. Just one star.
Oh yeah, well, because the star made this, Roxana. The star made that shell of blue you see around it. And the inside, it's like seeing this one star and saying, say you see this star here, right? And you say, okay, is there any other star in there? Well, no, it's just one star there. Well, again, this star could have been this star in another life, or maybe it will be soon or later. We don't know. But the thing is that this star, when it went into this phase where it aged, it became a red giant. And after it became a red giant, it started to slough off this gas. This gas just went outward. And as the star pulsed, I keep saying this, I know, but I'll say it just to drive home the point. As the star pulsed and grew, it would contract and it would grow. And every time it grew, another layer would kind of leave the star behind and form a ring around the star, or a sphere, we should say, an expanding sphere of stuff around the star. So it would collapse and puff out, and then that stuff on the outside might just keep going because it's not bound anymore with gravity to the star. And so over time you get these big concentric rings or spheres that come out from the star, and then when they're ionized by the white dwarf, the gas ionized, you actually get this glow. And with the Hubble Space Telescope, the details inside some of these planetary nebulae are just astonishing. There's so much going on in here. A lot of detail, a lot of very, very cool, knotty gas tendrils. Just an awful lot going on in here. You know.
Speaking of, You tried a longer exposure, and he did grab more detail, and you can see some knottiness in it right now.
That's correct. You can.
That 8 o'clock to 2 o'clock axis, there are two light spots there.
That's right.
At the 2 o'clock edge and the 8 o'clock edge. 2 o'clock is a little more prominent.
Yeah, right there.
Yeah, I assume that's implying some sort of an axis, whether those are polar or equatorial, I don't know.
Yeah, maybe. And it could also be, again, long exposures of some planetary nebulae will show these looking very oblong and different in size from one direction to the other. And then long exposures can sometimes blur that out. I shouldn't say blur that out, but remove it because it's so bright. That problem here is that we went for a longer exposure, and you can see some of this detail here is kind of has a little extra special detail to it, which is kind of cool. And down here, you'll notice it almost looks straight in a sense, doesn't it?
Uh-huh.
And that part of that reason could be because there's some density in the interstellar medium out here, dense atoms or molecules of other material, and as this expanding cloud strikes it, it's slowed down, or it's thwarted a little bit, so it might make a flat edge. Just like we see apparent flat edges in the Orion Nebula, we see flat edges of these gaseous ribbons. Well, those are caused because of the nature of how the gas is expanding and moving. It runs into obstructions, essentially, and that's part of the problem. But anyway, let me take us back to our wonderful planetarium view. Not planetarium view. I'm going to just try something else. And I'm going to go up to do a 1 minute shot still at only, I'm going to go down. I'm going to drop this down to 2,000. But 1 minute, so we're going to see a lot more detail if it's there. But it's also going to be pretty bright. So we're shooting 1 minute now. Hopefully it'll be a really, really nice object. Yep. Oh, 357 Smith & Wesson. Yeah, that's right, Trish. I actually fired a 357 a number of times, and in the movies, people just shoot me out, bang, 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 bang. You know what? In real life, that doesn't happen. In real life, it's bang, ow, pow,
oh, come on. I don't even remember how many 357s I have. Just takes practice.
Yeah, I guess. Oh yeah, 357 with snake shot. Yeah. Oh yeah. It's a good caliber for snakes. You're absolutely right. All right, here we go. Okay, now it's a little bit. Oh, look at that, Daryl. That looks kind of interesting, doesn't it? Okay, this shows us some more detail that we didn't see before. You'll notice, and again, I've got to rotate it, so I'm going to rotate it one more time. Here we go. Okay. So we zoom in on this now a little bit. I'm going to make you all sick here. Now look at, now you can actually see there's a distinct dark area right there. A little brighter. Let me get it a little farther in. Distinct dark area here, dark area there. And there's something here and lack of something here. It looks, and there's a bright knot right here. See that, Daryl?
Yes.
Everybody? So now we can see that there's some changes, there's some convolutions going on in this nebula. So that's pretty cool. And there's a lot of detail that we're not seeing here. So if I were to take about 45 of these shots, which I won't tonight, I promise, and then go to go into a stacking tool and then image process it, well, then we might actually see some pretty cool detail in there. This definitely is a knot of material here. There's no doubt about it. You can see that, and it's really nice. This little planetary is really cool. You should look up the blinking planetary. in Wikipedia and look for the Hubble shot of it, which undoubtedly exists. I'll bet you it looks pretty cool.
Is it too far for us? Too far for us to see?
What do you mean?
The blinking nebula? Why can't we go see it?
Oh, what do you mean? Go to Wikipedia ourselves?
No. Go with the telescope.
We're seeing it right now.
Yeah, this is what we're seeing.
Oh, okay. Okay. Never mind. I missed something then.
Okay. No, yeah, but I was just trying to say, if you look it up online, you can probably see if the Hubble took a photo of it and see the detail.
Okay.
Yeah, that's pretty cool.
Yeah, that's what I was wondering. I'm like, why would we go there if we could do it ourselves? Never mind.
That's fair.
Yeah.
You know, Daryl, I'm also seeing, and for those of you watching, I'm seeing there might be some more wisps out here. So that's kind of cool. Hey, Tammy Sublet.
Wow. Mark, you're not far wrong. I went ahead and looked it up.
Yep.
I'll post a link in the chat.
Okay.
That you see more is an understatement.
Yeah, it's probably got a lot more going on, huh? I don't see a lot going on out here.
It has a lot more going on.
Yeah, there's a lot out here that I kind of see subtle hints of it. I wonder. Of course, it's kind of low right now. I wonder if it gets up higher to the sky, maybe we might be able to catch some of that. So when we look at our planetarium, right? It's only well, actually, it's at 50 degrees up, isn't it? That's not bad.
No, it's a really bizarre looking object too. The Hubble image, it's false color, so it's greens and oranges and purples and all sorts of stuff.
Mm-hmm.
But they have a more conventional image of it also, and both of them are really something to look at.
Cool. I can't wait. Put that link in chat.
I did.
Oh, you did? Okay. Oh. All right. Let me just go. Oh yes. That image, it definitely does have some really, really interesting details to it, doesn't it?
Mm-hmm.
Yeah. And I think it's bipolar as well. I do believe it's bipolar. Very cool. Yeah, go ahead, Amanda.
I was going to say, I think you may have noticed some questions coming in.
Yeah, but it went so fast, I missed it. Because you put it in the Skype. And
Do wants to know if Vega is visible on the East Coast. I would say it is it not? I don't know at this particular moment, but...
You would be correct.
Absolutely, it's probably high in the sky right now.
Yeah, we actually were looking at it just a little earlier. That was the first thing we had in the scope when we came in.
Yeah, I guess you're on the East Coast, okay.
Yeah.
Sorry.
So
maybe I was thinking, like, I don't know, hemispheres or something rather than coasts. I don't know.
That's all right. That's okay.
And Roxana wants to know how close you can get to the nebula. I wonder if that means like zooming in with the scope or like.
Yeah, that's probably all it can mean, right? And if we zoom in, this is.
Well, in some of the. Some of the things we sent, like traveling past Pluto and stuff, I know they passed that snowman asteroid or whatever Thule was.
Ultima Thule, yeah.
Yeah. Have we ever come close to a nebula that way, or anything like?
No, nebulae
global cluster or anything like.
Nebulae are so far away that there's no way that we can even get to them. We can't even get to the nearest star. Never mind the nearest nebulae, which are like anywhere between 1,600 and tens of thousands of light years away. So it's really, a long way away. But look at how beautiful that is, huh?
Mm-hmm.
That's just beautiful, yeah. I know, we're sticking around, but I did this for you, Amanda, because you like this color, and you like the cat's eye, and so, Well,
that's what I thought it was at first.
Yeah,
actually.
Right. Well, it's again, these planetary.
It's mesmerizing on the screen. It really is.
Mm-hmm. Yep. They are indeed mesmerizing. All right, so that was the blinking planetary, and let's go see if there's another one. There was another one here, but I don't know if it's real. Yeah, see this one. Yeah, I don't know if we'll be able to see it. It's going to be kind of small, but we'll try it. We're head there now. Goodbye, blinking planetary. Phew. And we're going to go down to a star here to line up on, which will be Polaris again. This is the star that we're lining up on prior to our jump-off spot. This is the side, the depending on your point of view, the swan's right wing, and then it's going to move up to the planetary, which it has done. And now we'll take a discovery shot and see what we get. We wait a few seconds for the guide scope, the system, to actually identify and pull in a guide star, and then once it does, I think it's right here actually. I could be wrong, but we'll try it. We'll just do a lower, we'll do 20 seconds at 2000. Let's go. Oh, that's nice, Roxana. I'm glad you like this. It's a really beautiful color. It's one of the colors that the universe provides in the atomic interaction arena. Red is another one. Pink is another one. Green is another one. Blue is another one.
You are correct. The helix, I want to say it's in Aquarius, and it's quite large in the sky.
Yeah.
Actually, because of that, it's rather dim, but it photographs very well. It's a very beautiful nebula.
Yeah, it is. Here's another one. See, it's now instinct would tell me that this one's farther away because it's so tiny you can barely see it. Okay. You see how it looks so blue? Okay, all the stars have this again, we're in visible light now, and the blue of that nebula shows up like a sore thumb, doesn't it? Can't miss that. But it's very, very tiny amid all those stars. You know, one thing I thought of was, you have all these stars out here. Undoubtedly, some of them are stars like the sun. Some are stars that have planets. Many are stars that have planets, actually. And what if there was a civilization around this star before it went into this phase of its end-life existence? Now, isn't that interesting to think about what might have been the state of the technology of the inhabitants, if there were any there that had technology? If they were just microorganisms, then they would have been vaporized by the expanding shells of this ultraviolet hot gas, if not having lost their lives long before, hundreds of thousands of years earlier, as the star went through its death throes as a red giant, and prior to shedding any of its atmosphere. So if they were technical, perhaps they could have escaped. And when we zoom out and look at the universe, you see this, all these stars. There's a virtual panoply of stars here. Yet down here, at the very tiniest star, we could be witnessing the aftermath of a tragedy on the proportion of at the level of a civilization and not even realize it. So I just think it's very poignant to think about that. It's one of the reasons I got into astronomy, was because I wondered about those things. I wondered about those things. Whether a civilization, we're looking literally at the death of the death of a civilization at one point, because that star finally ended its life. If they got far enough along to leave, maybe they're not dead. Maybe they've existed for many, many millions of years, and maybe that star was not a no-brainer. Maybe that's not their home star. Maybe that was another star that they colonized planets around. So anyway, it's just kind of a neat thing that I go through and I think about. Weird as I am, yes. I'm a little bit strange. So, hey, what can I tell you? So let's see. Where are we? We did the blinking planetary. I
A
really...
little bit strange.
I'm sorry, you got something to say? Hello? Huh. I'm kidding. Yeah, a little bit strange. Okay, now we're going to...
Just a little.
Yeah, a little. I'm going to go see... Daryl, if you can use mute with that thing, that would help as well. Now we're going to go to Amanda's favorite little star. This is your favorite, Amanda.
Cat's eye?
You got it.
Yay!
The Cat's Eye Nebula.
For those who haven't seen it, you guys are in for a treat. If you like that blinking nebula, ooh.
Mm-hmm.
Stay tuned.
Well, you can already see it. There it is. It's right here.
I see it.
Yeah. Yeah. And let's just see if we can get some data on the Cat's Eye. It shows us a distance of 5,294 light years. So 5,300 light years away. So they had a really good way of gauging its distance. And it's also called the Snail Nebula or the Sunflower Nebula. Now,
no.
It's also NGC 6543, but we'll call it a Cat's Eye Nebula because that's one of its names, and because Amanda likes cats.
And because Amanda will pout.
Oh, Amanda will pout. Okay, she will pout. How do you spell pout? Okay.
I don't know. Listen, Trish wants to know. She says, so a nebula can show the beginning or end of something. Is that a correct assessment, would you say?
That is a wonderful assessment. Excellent assessment. Yeah.
There you go, Trish. You're getting it.
Trish, you got it. Yeah, and that's true. And so a nebula can show the material from whence stars are born. And it can also show the nebulas from which the stars are returning to the interstellar medium. So there's the Cat's Eye Nebula. Look familiar? Looks sort of like what we saw just earlier, didn't it?
Yeah. It's gorgeous.
Yeah,
it's so vibrant.
It really is. It really is beautiful. And this is, again, we are in white light. This is a white light view. Oh, Tina, Pewterball, I know you like Sirius. We all like Sirius. Sirius is the brightest star in the sky. So it's really, really beautiful. Okay.
And Mark
Arcturus.
is on mute. I'm not sure if he knows that or not.
What? I'm on mute? Oh.
I see.
I was on mute.
Moving. Oh.
I'm sorry, I was on mute. How long was I on mute? About 10 seconds? 20 seconds?
Yeah.
Okay.
Yeah.
Sorry, guys.
Well, I don't know. It got really quiet, and I looked over and thought maybe you were going to cough or something, but you didn't. And then I could see your mouth moving, so I decided to say something.
I'm glad you did, because I somehow went on mute. But I said to Tina, did you hear me say to Tina that I like Sirius too, but it's the brightest star in the sky?
I did not hear that.
Ooh, well then that's yeah.
Because I was going to say, is that something we can maybe view tonight? And Tim wanted to see... Oh, I lost it. Arcturus. Yeah. So Arcturus... I don't know if these are visible later on in the night, but I'm trying to jot them down as they come, guys.
No, that's good. They're visible now.
Okay. Well, but we just got here.
Okay, well, see, there's a little subtle glow here. We have a little bit of the observatory light in here. We have something over here, too, notice. And I just want to look on on our setup here and see what we've got over there. Let's get our frame size here. Interesting. It looked like there's a little galaxy over here. But maybe that's not a real thing. No, that's a real thing. Look at it.
Daryl, do you have thoughts on that? Is there a galaxy supposed to be around there?
I didn't see anything on the planetarium chart.
Yeah, I mean, neither did I. I'm not sure.
Certainly looks like something.
Yeah. Well, you know what we're going to do? We're just going to take a deeper exposure. I may have to move the dome, but in order to see that, I need to turn on my dome telescope system, or my camera system.
Mark, would you mind if I post a link to that apod exposure I think I sent you of the cat's eye recently?
No, not at all. That's beautiful.
Okay.
Beautiful.
That's an amazing picture.
Yeah, please feel free. You're always free to post links, Daryl. You never have to ask. It's all good.
You need to see some of the links I post.
I haven't seen your links you post.
Dole wants to know, why are the images of this a turquoise color, but other images of it are multicolored with mostly red?
That depends on the chemical composition of this particular gas cloud. If you notice this particular gas cloud, Dole, and I'll just show you just the cloud. Okay, you'll notice it has a fringe of red around it. Okay, and you'll notice that you're right, it's this turquoisey, greenish blue, teal type color. Well, that teal blue color is due to the element oxygen, because many of the stars can get to the point where they can make oxygen if they're big enough in their cores, but they also were made with the chemistry of the previous stars they were made from. What's that mean? It means that other stars that had gone supernova and created planetary nebulae like these, that's nice. These particular stars will actually, when they die, they will disperse their material to the interstellar medium. And when they disperse it to the interstellar medium, then it means that material can be used in the new creation of other stars. And that's exactly what happens. So you can have a star, for instance, that will actually have oxygen in its atmosphere, but it can't make oxygen itself. Or magnesium in its atmosphere, but it can't make magnesium itself. Okay? And this is exactly what we see in some of these objects. So when we actually look, for instance, at like when we look at the cat's eye, okay. Hold on. Let me go back. When we look at the cat's eye, then what we'll see is we might see this bluish green because that was in the outer atmosphere of the star. And when the star finally did slough off those outer layers in its later years, then we're seeing the oxygen that it was made with, not that it made. And that's a lot. We see a lot of that in our sun's atmosphere. Our sun is a moderate-sized star, not a very large one. Okay, and our sun's atmosphere has many different kinds of chemicals in it. It has calcium. It can't make calcium. It's not massive enough to make calcium. It has magnesium. It can't make magnesium. It's not massive enough to make magnesium. But it has a lot of these elements because it was made with those elements. And then those elements in its stellar atmosphere are turned into plasma. What's that? Plasma is just the atoms being stripped of their electrons and being left with just the protons and the atoms flying free. Okay, that's plasma. And so the outward radiation pressure pushes these atoms out into space. And these become the solar wind that we hear about. All right, and so that's what we see going on here, basically. We're watching this white dwarf, which is now the end of a star, and it's radiatively, very, very powerful with radiation, and it takes the materials that were blown out into space by the end state of the star, and it ionizes them. It turns them basically, it makes them into a plasma for a moment, and the electrons leave the atom, leaving just the protons, and then when the atoms recombine with the atoms, when the electrons recombine with the atoms, they give off light as they reduce their energy state to go back into the atom, and that leaves these colors. Now, when I say they return into plasma, that only happens with the atoms that are bound to the star, things like the calcium atoms, the hydrogen atoms in the outer envelope of the star. Okay, but we don't see too much. We won't see, for instance, that oxygen loses all of its electrons. Okay, it loses a couple of the electrons though, and then that will make this, have 2 electrons outside the atom, and then when they recombine, they bump into other things out there. They lose energy and they drop back into the atom or a different atom. Okay, but most likely that atom. They drop into the atom, and when they do, as they sink back into the different energy states, the locations in the atom where they are comfortable, they will give off light, and that light is a characteristic turquoise color, like this. All right, so that's why we actually see that with many planetary nebulae. It's just but again, it's a gorgeous color, but it really has some meaning. It means a lot. So there we got. You can see some extra shapes going on here. The cat's eye does have this really cool look, but we're kind of being robbed of seeing a little bit more. And the reason we're being robbed is because we actually need to reduce our ISO a little bit. We need to drop it down. So we're going to go down to 1,000. So we're going to cut that in half. Now let's go and do 20 seconds at 1,000. Yeah. And now we'll see, believe it or not, we're probably going to see more detail in that envelope of gas around the star. Okay. Because you'll see what it's going to look like now. And we'll have to move the dome, I'm sure. Yeah, see, look at. Now you can actually see there's more detail in here. And you can see what looks like these might be these shells of material that are blown off the star. See that?
I was going to say, it looks kind of like a swirl coming off the top going to the left.
It does, doesn't it?
Yeah.
It does. You're probably looking at...
I don't know if I noticed that before. That's weird.
Yeah, you may have, but you may not.
Just didn't.
But isn't that pretty? And you can also see it's got a little reddish hue down here. Let's go back, and we'll come right back to this in a second. Let's actually drop this down even more. Let's drop this down to a 400 speed. So it's going to now be really dim relative to this brightness.
Why do we want it dim? For stacking purposes?
We're for purposes of seeing some of the detail.
Okay.
Because it's still pretty bright in here, so I want to try and dim this down just a bit so you can see more detail. And by going to these lower values in the ISO, look at that. See, going to the lower values in the ISO, we see less noise. Look at that, Amanda. See, now you can see that ring goes all the way around, doesn't it? See that?
Yeah.
That swirl.
Mm-hmm.
And now you can see that there's like convolutions in here. There's actually more detail, and there's more near the center.
It looks more like the picture Daryl sent.
Yeah.
He sent us the link in chat, the APOD, and I mean, it was different coloring, but yeah, it looked much more like an eye, and it was kind of scary. I wasn't really expecting that, and I'm starting to see that image more and more as you.
Okay, well, I'm going to do a 200 now. I'm going to do 200 ISO or 200 sensitivity for 20 seconds. Now, keep in mind, we just did this, and this was 400. Now we're doing 200. It'll be even dimmer. And let's see if we've reached our limit when we get to that. Okay. What this does for us is it starts to show us at the fringe, you can start to see the red more clearly, see? But it's about the limit to getting our detail. So in other words, every object has a specific limit to how much detail it can show you. If we go really, really bright with this, okay, well, then we get this. But a lot of this is now overexposed in here. If we go less, okay, like this, look how much more detail is in here. So this is the magic number right here. You go at this exposure and do 20 or 30 of these and stack them. This will be a stunning object, absolutely stunning. So we'll do that later in the season, most likely.
Will you folks excuse me for a moment?
Sure, Daryl.
Sure.
So you see, this is Amanda's cat's eye. We should just call this Amanda's Nebula.
Ah, sweet.
We should. You know? Why not? We should just call it Amanda's Nebula. Okay, so now let's go see it. So that's the cat's eye. We just looked at it, and I know that we had a request for Arcturus before. And I would like to see if we can see Arcturus, but it's going to be over here, right down here. And I'm guessing that the dome is going to be in the way, but I can move it. So let's go to Arcturus for...
and I recognize the name, but I can't think of the mythology at the moment.
Oh, you're talking about Arcturus? Isn't he the herdsman? Or is he shepherd? I can't remember now.
Okay.
Well, now you're going to have to look it up. Jeez.
Alright.
I can't remember. Now, Arcturus is only 36 light years away. Okay? And we did just have something fly through. You did see that. It wasn't your imaginations. Something just flew through there. And the dome's in the way because you can see these spikes here. These are diffraction spikes caused by a straight edge. That straight edge is the dome. So if I take a picture of Arcturus for 20 seconds at 200, we're probably going to see some domage. Which I'm doing. I'm taking a picture anyway. Because, hey, we had Arcturus as a request.
The Bear Watcher. Or Guardian of the Bear, because he's looking out over Ursa Major.
Mm-hmm. Okay. Yeah, see, there is Arcturus. It has a spike on it because it is actually got a piece of the dome in the way. I was just reading what you wrote there. You wrote Greek, man. I was like, wow, hey, you're good.
I had to edit a little bit because it didn't fit.
Okay. Good night, Tara.
That's just...
Tara's heading off. Hey, Bobby Burgess, how you doing? Yeah, you missed the moon. But you know what, Bobby? I got I have images of the moon, but
From tonight?
Yeah, earlier. But the thing is that I've got to go hunt them down, which I can do, right? That shouldn't be a big deal. Here, hold on. Let's see. Let me go look. Alright, just a second.
I was just about to say, at least we can look at Arcturus while we wait, and it just disappeared off the screen.
No, it only disappeared because of one reason only. That's because I took a picture of the moon that I wanted to show you. See, this is the moon from earlier tonight. Okay, it's really looking pretty. Yep. And it was low. It was just setting over my house on the western side. But if it's clear tomorrow, we'll see it again. You know. Anyway, this is all visible light so far tonight. We're looking at visible light. We're not looking at any other filtered light right now. I'll just let this sit here so you guys don't get like sick to your stomachs here. Here we go. So that's pretty. So that's how much of it was illuminated. A small amount. Cool.
I'm hearing George Harrison in my head.
Why?
He has a song called Here Comes the Moon.
Well, you can't sing it or I'll get penalized. Cool. All right,
Let's just not have the stream go on till I sing Here Comes the Sun.
Can you hold us together while I go move the dome?
We'll see.
All right, I'm leaving now. Don't do anything I wouldn't do. I can't hear what you just said, so...
Chat flies into chaos. Maybe Daryl will come back soon. So I hope you guys are all enjoying this. Too bad Mark didn't take a closer shot of this. Oh, welcome back.
Thank you. What are we looking at now?
We were going to Arcturus, but now he's going to move the dome, so... Does this look like Arcturus to you? Maybe we didn't get there.
Yeah, it looks like Arcturus to me.
I'm not sure why he's moving the dome then. Maybe to see Sirius after?
No, Sirius is, oh goodness, Sirius isn't up right now.
Oh. Okay, I'm not sure why he's moving the dome, but this should be Arcturus.
Yeah. It might just be
Tim
close
requested that.
It might just be that it's close to the edge of the shutter. It definitely is now. I see the red on the screen.
Yeah, so do I. Okay.
Yeah.
Well.
Arcturus is a bright star that's a little bit west of Vega. It's very similar in brightness to Vega. It's actually just a little bit, it's a hair brighter than Vega. I believe it's the fourth brightest star in the sky. It's in the constellation Boötes the Herdsman.
Yeah, we just looked up. It's the Bear Watcher, the guardian of the bear, because it's looking over Ursa Major.
Well, it's the Herdsman. People may call it the Bear Watcher, yeah.
Huh.
It's a different spectral class than Vega is. It's more of a yellow star.
Yeah, well, I would have said orange. You guys are saying yellow, though.
Yeah, something like that.
Yeah, usually I call it a different color than you and Mark do. Even if it's not like yellow to orange or whatever, but...
Uh-huh. There's 10-foot tall Mark.
Mm-hmm.
Hello.
Hello. But you're saying... Because, okay, I think I misunderstood something. I thought you said it was like a fourth brighter than Vega.
It's the fourth brightest star in the sky. It's actually marginally brighter than Vega is.
I thought Vega was the brightest.
No, Sirius.
No, I guess Venus is the brightest object in the sky, no?
Yeah, but it's not a star.
No.
Sirius is the brightest star in the sky. It's in Canis Major, the big hunting dog,
Okay.
or the big dog, and that's southeast of Orion. Vega's probably, or excuse me, Sirius is lost in the morning in the sun right now.
Yeah.
Arcturus is the fourth brightest star in the sky. It is just a smidge brighter than Vega is. Most people couldn't tell the difference by brightness, but a lot of people think Vega looks brighter because it's a blue star, while Arcturus is a yellow star. But Arcturus is actually just marginally brighter.
That's right. And we were heading for Messier 13. And I discovered another issue with Messier 13. It's another one of those objects that you see a star for a few minutes and then it goes hunting again, because it's like it actually has a problem trying to find it. So it tries to locate it, and then it should be able to figure it out. And I think it does. I think it has. But I'm going to go into a 4K mode here and bring this up. Get us up there to see. Yeah, see? It's not there. It's not there. It doesn't know where it is. There's something about it. I thought it was my telescope or my setup, thinking it was me the whole time. It's not me. It just doesn't know what it's doing. There's certain objects that it just can't, it just doesn't get right. It has bad data for them, and I'm figuring it out. I guess when you're looking at them all the time, right, it stands to reason that you're probably going to find the ones it doesn't work with. Okay, so see, that's where that is, and where the telescope is pointing is way out here. So we're going to do this. We're going to go to this star right here. Okay. We're going to go to Eta Hercules. And Eta Hercules will be right there. That should be Eta Hercules. And let's see if Eta Hercules is the problem. If Eta Hercules stays here, then we know that it's not Eta Hercules that's the problem. Okay. Okay, so Eta Hercules is not the problem. So what we're going to do now is we're going to head south.
When you see that shape in the planetarium view, that kind of oblong rectangle, that's called the keystone of Hercules.
That's right. This right here he's talking about.
Yep. And it's like the keystone in an arch, you know. That's that wedge-shaped rock at the top of a stone arch that helps hold the entire arch together.
Mm-hmm.
Called a keystone, and because it's shaped like one, they call it the keystone of Hercules.
Yep, that's right. And it's really supposedly this.
Sort of like an upside-down Orion, but dimmer.
Yep.
And only 2 stars in the belt.
Yep. All right. So we have our cluster right here. So I'm just now going to move it in, bring it over closer to us. If I can just go the right way. So, okay, we know the Ring Nebula. If you go to Sulafat, the Ring Nebula has an issue. Can't find the ring from Sulafat. Messier 13, can't find it from Eta Hercules. It's got the wrong data. Really strange, really odd. Okay, first things first. Let's go and get a focus on this one. To do that first, we're going to have to bring this down. I guess.
I never saw you have an issue finding M13 before. Is that only from that star, Eta Hercules?
Yeah. It does that weird issue, and if it goes to Eta Hercules, then I know it's not going to work. And it went to Eta Hercules, and it didn't work. Very strange indeed.
Is that a Stellarian issue?
I don't think so.
But only from that one star.
Only from that one star.
Huh.
Yep. Okay, so here is the focus view. This, I've got it really, really magnified very brightly, as you can see. Okay. And, or very, not bright, but you know. So I'm just going to now focus. And you'll see them go out of focus. And back into focus. Doing this dynamic focus here. I'm going to try and get this right. Okay, back out of focus. Actually looks pretty good. Let's try that. And now we're going to bring it up into the view. And yes, I could have made it so that I can... By the way, we have clouds out there, just so you know. I'm going to show them to you in the all sky. 1600 for 20 seconds on the Great Star Cluster in Hercules. Let's hope that the guide star was found. I don't like it when clouds show up out of nowhere. I tell them to go away. They don't listen. They don't listen to me at all.
George Harrison also has a song about clouds.
Look at this. Wow. Oh, look at this, guys. Now that's a beautiful cluster. Wow. Daryl, would you be so kind as to point out the propeller one more time?
Okay, if you look at the center of the cluster, look to its lower left at about 8 o'clock. Right there, that's one of the 3 legs of the propeller. Right there is the center, there is the upper leg. and then the lower right leg right there.
So that's the 3-prong propeller that is known as the propeller of M13, Messier 13.
And I didn't just make that up. That's a well-known, I don't know what you'd call it, an apparition. Not an apparition because it's real, but...
it's not an asterism because, well, it's a... Maybe it's an anti-asterism. It's the lack of stars, right?
Feature. Let's call it a feature.
Yeah. Amanda, do join Roxana's music page, by the way.
I'm working on it right now.
Good.
Well, I'm going to add her on Facebook first.
Oh, you add her on Facebook, and she'll certainly want to talk to you. Thank you for asking, telling her about that, Roxana. I think she'll really enjoy it. Look at this, Daryl. My gosh, this is so beautiful.
Yeah, it is.
Wow. Now,
somebody asked on another stream, could that be like dust clouds or something? Globular clusters tend to be so old; they're billions and billions of years old that I would not expect a globular cluster to have dust clouds in it after billions and billions of years.
Yeah, me either.
But what it is, I'm not sure offhand. I'd have to try to look it up.
I think that it could very well be that it's just because of the nature of the fact that this is a halo object. It's constantly in flux. It's always moving. Its stars are always moving relative to each other. And maybe this is just one of those points where there's fewer stars here and there and there. And because to us, we recognize this shape, okay? I mean, it could look like a Chinese throwing star, a 3-bladed throwing star, too, for other people, I guess. But it really, you can almost use pareidolia to see shapes everywhere else you look in this cluster, with other things, too. You know? I mean, using pareidolia, you can say, look, this is an exact straight line right here, an exact straight edge right here. Is that an exact straight edge or there or what? I mean, it looks just like a straight edge. It's just how the stars appear at this moment in time. But imagine them in motion. They're all doing this. They're doing this all the time. They're moving all around. So the cluster is moving through space, around the galaxy, and all of a sudden, we see this snapshot for all of our lives. And the lives of those who come after us for several hundred years. But over time, there'll be subtle differences in locations noted for where these stars are located. You know, look at that, though. Oh, that's beautiful.
It is.
And you can actually see, this is, again, in real color, so you can see how yellow the stars are. There's more yellowy stars, and this is almost overhead. So we're seeing that there's some bluish color, but many of the stars are yellow. Now, that doesn't mean that there's hot young stars in here, because they're not. It just means that the combined light is just fooling the camera sensor. This is really more of an older cluster, as are the clusters that we see with the globular cluster world. You know, they are actually among the oldest clusters in the entire universe. They're so old, in fact, that they don't have elements beyond hydrogen and helium in their compositions. They tend to be kind of pure in that way. Now, as astronomers, we have this way of being very, very difficult on all the people that aren't astronomers. We say that anything that's not hydrogen or helium is a metal. Well, that's not true, obviously. We know calcium isn't a metal. Okay, we know that neon isn't a metal. Okay, but we do call them metals. And it has to do with the periodic table. There's a little bit more to it than that. But the fact is, globular clusters only have stars that have hydrogen and helium in them. Now, if you see a globular cluster star that has more in it than we know that these have, then it's possible that on its trip through the galaxy, it picked up a star or two or more. And on its way out, it may have shed a few. Maybe these stars out here are in the process of being ejected by all the gravitational interactions going on. Or maybe they're in the process of being attracted to the cluster, or maybe both. A lot of this could be going on. We could have zing, zing, zing going on, and zoop, 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 where they're going in. That's zing and zoop, just for those of you that might want to, do that on your own. So that's a possibility, because these stars do plunge through the galactic disk once in a while, and when they do that, they're gonna be either shredded or they're gonna be gaining more stars.
Globular clusters, though they do tend to be old yellow stars, again, some of the oldest stars in the universe, are globulars known for having what are called blue stragglers?
That's correct. Blue stragglers, it's correct.
And where do they come from?
Well, when you think about blue stragglers, right? When we talk about blue stragglers, like in astronomy, and you look at I'm gonna tell you what they are. I'm gonna tell you basically exactly what they are, because I don't want to. Okay. See, globular clusters, the stars in the globular cluster, they're all doing something that we know very well, and that is they are fusing hydrogen into helium. Okay, but sometimes in a globular cluster, you'll find stars that are a lot more luminous and a lot more blue than the other stars, and these are called blue stragglers. Now, what that means is, and they're stragglers because it means they haven't reached what's called the turn-off point yet. The turn-off point in the main sequence diagram. That is, you have that ribbon through the middle of all the stars that are doing from O stars all the way to M stars. Okay, you have this ribbon of stars that are doing nuclear fusion that we know, normal hydrogen fusion, and that can be accomplished by turning hydrogen into helium. Okay, just like we see in these globular clusters. But the
main sequence.
That's correct. The main sequence is the stars that are converting hydrogen into helium. That's what normal stars do. We're looking at that going on in this globular cluster right now. All right. But whereas some of the stars have reached that turn-off point, there might be some that have not. The ones that have not reached that turn-off point are going to look a little bit more blue and be more blue and luminous than some of these other stars. So those are the blue stragglers. And the blue straggler family of stars is something that is also very interesting to talk about and very interesting to consider doing research on. I just think it's pretty cool. And the first blue stragglers were found by Alan Sandage rather, back in the 50s when looking at these clusters. It's really neat. He was actually performing photometry, which is actually what I did for my my thesis work in astronomy, was looking at the light that's being sent to us from the stars. By examining the light, we can actually do some really cool things. For instance, I found hot blue stars speeding out of the galaxy. I found these are blue runaway stars, they were called, runaway B stars. And so that was my thesis in astronomy, was runaway B stars. Just a really neat thing. And how do they relate to blue stragglers? Well, those particular stars don't relate to blue stragglers, but it's just that the blue straggler is just a really odd star to have in a cluster of very old stars, and you can't miss it. They are blue, and you can visually see that some of these stars look like they might be bluer, but the blue straggler is maybe it's some of these stars. I don't know in particular whether any of these stars are true blue stragglers, or whether we're just looking at a combined light effect going on there. I'm not sure. Again, we're taking pictures with a camera that has a special sensor. So I don't know, Daryl, if that's going to be sufficient for a guy of your caliber. But
that's fine. Well, I've always wondered, they say when you look at a galaxy, the stars we see near the center of the galaxy, in the nucleus, they tend to be older yellow stars.
Yeah.
And the bluer, younger stars tend to be out in the spiral arms where the, more recent star formation is happening.
Yeah, that's true.
That might relate as a general thing.
Yeah, and that's typically what we see in galaxies, But I think that part of it has to do with the densities of the stars in a globular cluster. If you look at the way they actually move, the way they actually move in a star cluster, if we could map their movement over time by looking at their motions within the cluster, then we see that these blue stragglers do very, very intricate motions within the cluster, and they're actually part of. They're very much important to actually. They're very important to how the cluster actually moves and morphs throughout time. So I think that's something very important to look at, and I'm sure that we can do more of that. Now, the blue color in here may be, again, due to these bluer stars, but Sandage had only just discovered them, in the 50s, and we've been studying them for obviously many, many decades. But that's a beautiful cluster. Gosh, I just can't get enough of it. I mean, and of course, I have like I said, I'm using a new focus technique. One of the other things I'm using, which you guys don't know about, is I have, since we had our last stream, today I incorporated the new telescope operating system, not operating system, but the observatory control system. So right now, in the telescope, I have this brand new system that I wrote. It's a system that I did. It's a circuit that's going to run the telescope out in the desert. So let me, maybe I can show you some of that real quick here. How would I do that? Yes, I go here, and let's see if I can just flip off. I go manual and turn off the IR. Oh, there you go. Okay, so you can actually see I have a blue. There's a red light in the dome now, and there's also a blue light in the dome now. That red light is actually sort of looks ghostly, doesn't it? But it's actually, that is the circuit that I wrote that's actually controlling the telescope in there. That thing can control the cover on the telescope. It can control the roof. It can control it can control the rest. Well, it controls the let's see. It controls power to the telescope. It controls the roof. It controls the open and close of the cover of the telescope, and a variety of other things actually. And so it's definitely, going to be something that's going to be a figurehead, monumental importance to this particular scope, making sure that everything's working. If I zoom in on this, I'm not. Well, you can't really see what's going on there. You can see that the blue light is actually blinking. It's not blinking, but kind of like dimming and brightening a little bit. That's another thing that I wrote into it, which is important. So Roxana asked a question. So blue is young.
So did Katie.
Huh?
Let's not jump the gun. Katie asked a question first.
Okay, and what was
Roxana. Katie wants to know, would it look much different if we could view it as it is now?
Meaning the cluster.
Yeah.
Yes, the cluster would look very different because those stars will have had 30,000 plus years to move. If we go back to this cluster and we go and look at this image right here, right, and we bring up, we zoom in a little bit, move it a little to the side, and then bring up our data on this cluster. Let me first of all get the cluster. All right, great star cluster. This is actually we're looking at 22,000 light years away. So you're going to be seeing this as it was 22,000 years in the past as we see it now. But when we actually look at it, say as it is now, they will have had 20,000 years worth of motion to get rid of or to change the way the cluster looks to us. And that's
would it be fair to say that it would look different in detail because star positions have changed, but as a general thing, it would look much the same?
Oh yeah, generally it would look like a globular cluster, but the propeller that you see here, okay,
yeah.
this propeller this little thing would be gone. You wouldn't see that because the density, the knots of the stars that are causing that to happen will have changed. These stars in the outer fringes might actually be farther or closer. The blue stars inside, the bluer stars, would actually be farther or closer. These blue stragglers, they have orbits, and they actually do kind of make up the morphology of these clusters, very much so. So I think it goes without saying that, yes, Katie, it would look very different if we saw it just as it is right this second. And what was Roxana's question? You're on mute.
I don't know if I was on mute. I know. Roxana wanted to know, so blue is young and yellow is old. What is true about other colors? Because you were talking about the spectrum, and that is for heat and brightness and stuff.
Well,
but now she's talking about, because you said, with the blue stragglers being younger and the yellow ones in the middle being older stars.
Yeah, but that doesn't necessarily mean older and younger, though, and I have to explain that. But go ahead, Daryl. Say what you had to say.
Oh, I was just going to say, you could say red is smaller.
Lower temperature. See, it really is about temperature, Roxana. So, blue stars are hot. Red stars are cool. Hey, man, they're cool. But, it's also cool in temperature. But you see, if you look at the globular cluster, yes, the stars are yellow because they're predominantly stars that are of that temperature, right? But there are some stars that are hotter and more luminous, and they are going to be bluer. So it really isn't about the age, but they are amongst the oldest clusters in the universe, on top of everything else, all right? Because you can have a cluster full of G-type stars like the sun, and they're going to be kind of a whitish yellow. All right, you can have a cluster of M stars, and they're all going to be red. And those M stars might be younger than the G stars. It's just, or they could be much more old. The thing about the M stars in particular, and not to confuse you, is that, well, let's talk about stars in general. Every star type. All right, if a star forms, it doesn't necessarily, in fact, it won't start, for instance, as a hot blue star and then become a red star. Like a small red star, like a red dwarf. It won't do that. See, what's confusing about the astronomy is that there's stages that these massive stars, middle mass stars, lower mass stars, and tiny mass stars all go through that at some point or another make them look similar to each other. Okay, and that is confusing. For instance, the sun is a G2, a G-type star, the second level, G01, third level, G0, G1, G2. Okay, and so we're kind of a whitish yellow, a little more yellow. Okay, and the star, when it runs out of its hydrogen, it's gonna bloat into a red giant. Now, why did I say red? Well, because as the star bloats up larger, then those hot layers that are close to the star now, which are a brighter color, the G-type color, as the star expands outward, those outer layers are going to cool, and it's going to end up looking like an M star. All right? It's not going to be an M star like a small M star. It's going to be a red giant, but an M-type star. So the letter really has everything to do with the temperature, and it's temperature that causes that color to change. It's not that the star is, fusing different things here or there. It actually has to do with the fact that the star's either bloating in size and becoming redder, or it's shrinking in size and getting more toward the blue end and bluer. There's a lot of ways in which the star's color is affected, and the radius of the star matters. If the star's radius increases because it's bloating, then those outer layers are going to get redder and cooler, and so because they're farther away from the center, they're going to get cooler, and that's going to make them redder. Okay, and as the star contracts, it can get hotter again, and those layers will go from a cooler red looking color to more of a brighter color, a color that's hotter, indicating like maybe instead of an M, maybe it goes to a K or a G or even an F. Okay, maybe even it might, if it actually shrinks, if the star finally does shrink down to a white dwarf, well then it becomes its own special type of star, but it's hotter than any other type of star at that point. So it's really, astronomy is really full of all these amazing conundrums and things that we just don't understand the full gamut of, including the evolution of these types of stars. We understand star evolution, yes, but we don't understand some of these intricate details. For instance, in the center of the Cat's Eye Nebula, we saw this star. It looked like a star. It was actually a white dwarf. Or was it? Now, white dwarfs are again, very hot. Yes, hey, look at this one. Hey, what do you want? I'm doing the Italian thing, he says. But my mother was Native American, so what does that mean? It means I'm missing my hatchet or something. I don't know. When we look at the stars in the cluster, right, and we look at how those stars evolve, these stars that are cooler, all right, they can last a lot longer than the stars that are hotter. And the stars that are hotter and bluer tend to have shorter lives. And they tend to plunge lots of stuff back into the interstellar medium. And especially if they go supernova. But stars like the Sun do like the Cat's Eye Nebula. It puffs up these outer layers and sheds these outer layers, then it contracts again, then it puffs up again and sheds more layers, contracts and puffs them out. That's why we see what look like many layers coming off, like onion skin, when we see things like the Cat's Eye Nebula. It's just the way that the universe works, So when we actually when we look at, say, the Cat's Eye over here, okay, we actually see the star has blown off these layers. Now, this star is actually it's a white dwarf. Okay, it's very hot. Like I say, it's 50,000 Kelvin at the minimum, and that white dwarf is the end state of a star. It means that this star is going to live out its life now as a white dwarf. It could never become any other type of star, and it's a special case star at this point. It's a white dwarf that's actually going to ionize this gas until the white dwarf itself cools, and then it becomes a black dwarf at some point in the future. And then, of course, the gas that's being illuminated will not be illuminated anymore, but that'll end a lot sooner, because the white dwarf will cool below the level at which it can ionize the gas, and that gas will just go dark eventually. It'll still move out and away from the star. For time, it spreads throughout the universe. Next thing you know, other stars are being formed from it. Other planets are being formed from that, right? From that stuff. And next thing you know, maybe some alien life is formed from that as well. And now, there lies us. That's where we came from. And Carl Sagan said it best: we are made of star stuff. And star stuff is is the rejoinder that I always use when I tell people, where do we come from? We come from star stuff. Carl Sagan, my favorite astronomer, told me so. But it's actually true. Every atom in our body was made in the heart of a star. There's not one atom in our body that was not. They were all made in the heart of the stars. So this is something that, well, I say except hydrogen, maybe. There's enough free hydrogen in the universe that maybe some of that was in the primordial solar nebula before all the planets formed and so forth. But isn't that incredible, though, when we look at these things? And so, in this case, we see, let's talk to the hand. Talk to the hand. In this case, we see the death of a star. All right. And in this over here, we see a bunch of stars, tens of thousands of stars. And what's funny about globular clusters, and this is something that no one can explain. You would expect it because these are the oldest stars in the universe, that maybe somewhere in here we should see one of these planetary nebulae. One of these stars has to have died sooner or later at some point, right? So we should find a planetary nebula in there from a star that maybe died. But the truth is, they're very rare. There might be 6 known planetary nebulae in a globular cluster. And we don't really know why. Isn't that great? I mean, that's kind of a cool thing. But anyway, I digress.
No, people in chat are loving it.
And Amanda is their spokesperson. That's good. That's good.
I'm keeping an eye on things.
You are. So that's what I like about, astronomy. That's what makes astronomy so worth it to me. It's because, remember, we only have the light from these things. We only have the light that comes to us from these stars to see. We can't touch them. We can't sample them. We can't fly a mission over through it and just grab a sample of the atmosphere. Okay? None of that. We can't do that. We just have the light. The light we see coming from the stars is all we have. And from that springs our entire theory of the universe and what the universe is made of. I'm going to take one more shot. I'm going to go down even more. Go to 1,000. Let's see if I can go. I'll go 30 seconds at 1,000 with the Messier 13. I just want to see if I can get one good shot of it. And then I'm going to start up the Oculus, which is the camera. All sky camera. Yes, do that. We're going to go 40 seconds and save the image and definitely add the auto processing as I decide what that's going to be, and go. And now we'll wait and see what we got. Meanwhile, let's go see if the image looks how that looks. Wow. I just really like this cluster. That's a little bit of walking going on there. We're going to try that one more time. Yeah. But man, this is just... See, that's the difference between this and this. Okay, a little bit of motion ruined that one, but this is beautiful. So now we'll see. We'll do another 1 minute shot. Okay, and we can see some clouds here. This is my shot right now. I'm gonna go and we're gonna do a stretch here. First I'm gonna activate it. Okay, now I'm gonna do my stretch. Okay. Yeah, you can see we got clouds all over the place there. See them?
You see them at the bottom.
Yeah, well, they're here too. See right
Right.
there? Oh, well, I'm in the bottom too. I'm in the way.
Oh, I didn't think you were a cloud.
Wait, no! Wait a minute. That's better. Okay, yeah, up there you see there's some clouds up here. Okay, right there. And down here, they're all clouds. Yeah, and over there. So we probably have light cloud cover all throughout. But we'll try it. We'll just see what we can get, you know. Wait, what are you doing? Hey. Just kidding. So anyway, with that said, that's better right there. That's much better. So taking them through light clouds is star clusters. You can take through light clouds and kind of do okay. Hey Keisha, how are you? Keisha Fowler's here. Keisha Fowler. I love it. Glad to see you. Okay, so I'm.
Not everyone gets a song when they make an entrance.
Well, you know, I mean, I think it's nice to hear from people that are joining us, you know, and
Definitely.
And they'd like to hear from you, right?
Mm-hmm.
Yep.
Which is an awesome mod over at Agenda Free TV. It's another chat you should be safe at if you want to go visit ever.
Awesome. Oh, by the way, I mean, I didn't even say what happened. You know, when I went out to Arizona. That's not the only place I went. I went to Boulder, Colorado first. And
yes, that's right. I figured you were going to talk about that.
I forgot. I'm sorry. No, it was I did the show Beyond. Well, first I was there most of the day. I did the show Deep Space with Sid Goldberg at Gaia TV, and then I did the show Beyond Belief with George Norrie. George is now the new, Coast to Coast host. Not new. He's been there for many years. He replaced Art Bell, and George is.
Well, you want to rephrase that? I don't like the replace. No one can replace Art Bell, but yeah, he snaked his way into the company. But sorry, I won't editorialize. Go on.
He was given the job of host for Coast to Coast. So, I met the guy twice, and so he is who he is, I guess. But I did his show Beyond Belief at Gaia as well, and so those shows went well. And then from there, I was supposed to go to Arizona. I would have still been in Arizona doing the observatory, but unfortunately, with COVID, I had to cut it short, and I'm going back July 13th to actually build the observatory finally in the desert, and I'm going to be sending out everything, all the equipment here, and in that time frame. So I mean, July 13th is not far away, folks. The 15th is actually the build date, and then when I get out there, I'll have all that equipment out there. Then the pier is going to be welded together and made out there, and then we're going to be able to put all the equipment in, get it up and running, and before I leave, the goal is to be doing live SkyTour West before I leave. There's a lot to do. There's got to be people who put on garage doors are going to come out because they're going to put in the rails. I got people that are going to put in the posts to catch the roof as it rolls off the building. And that mechanism to roll it off and on is mechanical, could run through the computer. I've got it set up now. And it will do the job that I can't do with the dome, because the dome has to rotate and then open the shutter. And it's really hard with this telescope the way it is, because it has multiple telescopes mounted on it, and it makes sort of a vertical aspect ratio, and the slot sometimes is at a weird angle, and the telescope can't quite get all three telescopes to see out at the same time. So the dome is not the best thing for this type of telescope. Anyway, and there are fires. Yes, KDQ. I have photos of the fires, and I watched the slurry plane, which is a DC-10 converted to carry these things. This fire retardant. I saw it flying over the fires and dropping retardant. It's pretty impressive. So it goes up and then it lands, fills up, goes up, drops it, lands, fills up, goes up, drops it, lands. I mean, all day.
Yeah, we had the DC-10 here when the Black Forest fire happened back in 2013, I think it was.
Wow.
That was really something to see. And you don't want to be under that thing when it drops a load.
No, actually, that would probably be pretty painful, actually.
Yeah.
Because it's not that the stuff is going to sting your eyes or anything. It probably will. But there's a lot of force. If you watch how they drop, they fly down. I imagine a whole passenger jet now converted to dropping fire retardant. It flies over the contour of a hill, flies down, and releases, and then goes up. And that's imparting, 225 mile an hour speeds to this fire retardant that's heading down to the ground. It's not just gonna drift down to the ground. It's gonna slam into the ground. And if you're under that, I mean, it's gonna knock you on your butt. It's gonna knock you right down. It might knock you right out too, as far as I know. I don't know how much force there is, but it's pretty crazy.
Plus, you'll have to take a bath afterwards.
Oh yeah, it's all red.
Will you be streaming any of the building of the dome or anything?
Oh, as best I can, yeah. Because see, I gotta take the computer and send it out. I got the monitor to send out. I got the telescope. The pier staying here because I'm putting the old telescope back in, all refurbished. We're gonna have great views with that. And then I have to send the materials to make the new pier, which I've got here. I'm gonna send, and I have the observatory control circuit, which you saw in that blue glow. I mean, it almost looked like almost looks like the Cherenkov radiation there and coming out of the dome, the blue glow. And then I have to send all the other equipment that goes along with the telescope, which is, of course, the telescope, plus the mounted telescopes, plus the control circuits, the filter wheel, the cameras. I mean, everything's got to go. And then, I mean, that's where the tire meets the road. When you don't come back until that's in place and installed and operational. Today I went through a study to make sure that all of my components can handle high heat. Because in the desert, inside the building, the temperature could get up to about 130, 140, and that's pretty hot. So we want to try and minimize damage to the telescope gear, and I'm sure it'll be fine, because that's, as hot as that is, it's not in the range of the components. The components can be a little warmer than that, but I don't want to take any chances.
Okay, I'll be right back.
Okay. In this all sky down here, this is Jupiter and this is Saturn right here. But it's not going to be possible to look at those without moving the dome, number one. Number two, we're not going to be able to see very good views because we're actually looking through light cloud cover all over the place here. Of course, I say that, and this Messier 13 doesn't look that bad. It's not bad at all. But maybe it's because we're actually looking in a way that's in a location that doesn't have a whole lot of clouds. But I'll find out and do it again.
Mark, when you build the dome, when you build the observatory, not the dome, like the sliding garage doors, Are you going to have skirts on them so, to keep dust out?
Absolutely. There's going to be skirts that are actually going to be on the actual roof itself. There's going to be a skirt that hangs down about 22 inches. And these 22-inch skirts are going to be used to basically keep any dust out of the dome. I keep saying dome. Out of the building. That's very important because, we don't want to have the dust get on the telescope, number one. But it's not the telescope I'm worried about as much, believe it or not, because it's going to have this mechanical cover that comes on and off with the motor. It's the computer. The computer is going to have a coolant, potentially a liquid coolant. And if I get a liquid cooler, that'll cool the main processor. But if there's any dust that gets in there and gets into the workings of the computer, it could short out stuff. It could ruin the motherboard. It could ruin things. Can't have that. I gotta figure out a way around that. Now, I did think of a way. I could say I use the entire observatory is being run by Arduinos, and for those of you those that know that, you go, oh wow, because you know what they are. But Arduinos are little tiny microcontrollers. They're this big, and they can be used to do a variety of tasks. I'm using one Arduino to do 5 different tasks in the observatory, including rolling off the roof and running the cameras and the telescope, all that stuff. But as far as the Arduinos go, the other thing they can do is they can activate little switches, solenoids, which are little, basically think of them as clickers to activate a bigger circuit, okay? They're switches, basically, to maybe activate a bigger circuit. And that bigger circuit might be attached to an air compressor to do like canned air would normally do. The only problem with that is that you could actually have a problem with debris coming out of the nozzle rather than just air. And so you've got to be really careful with how you filter that air before you spray it out. You get oil from in the compressor on the lens or on the end of the telescope, and that's a showstopper. So there's literally a ton of things you got to worry about. So I'm thinking maybe if I can't do the air, I'll have to do something else. But the best defense against that is to make sure that that telescope can't be covered by dust in the first place. And so you need to actually have the telescope covered with, that is to say that the cap on the end gets covered. It gets coverage, and so does the other telescopes. So I have to do that. But that's tomorrow. I'm going to make those parts to do that, and I could have this thing installed within a day or two if I can just, make sure it all gets in place. Yep. So anyway, so I will have skirts, yes, Daryl. And then these other things that'll protect from further dust problems. Okay.
I figured you did. I just didn't know the details.
Yeah, it gets more and more elaborate every time I think about it, but it has to happen. Yeah.
Tail grows in the telling.
Yep, that's right. Now, see what's really cool here is that, this right here, that looks like a cloud. That's actually the Milky Way.
Yeah.
And we have clouds all throughout here, so we're mixing clouds and Milky Way. But hey, you know what? I wonder. Yeah, I don't know if it's up high enough. You know what I'm thinking, right? You know what I'm thinking, Daryl, yes?
Not offhand, no.
I'm thinking about the dumbbell.
Oh. Mark, I hope you and Amanda will forgive me, but I need to go.
Daryl, that's fine. You go right ahead, man. I appreciated your company. We're going to be closing down soon anyway, but I want to try one more object here.
Sure.
So, okay. Thank you for joining us. Have a nice evening, Daryl.
Yeah, it was wonderful, Daryl.
You too. Y'all, thanks for having me on. Good night, everybody.
absolutely, Daryl. You have a good evening, okay? We'll talk to you soon.
Thanks. Take care.
Bye-bye.
Bye. Have fun.
Yeah, there's Alberio. We might squeak by here. I don't know, though. I can see... Well, it's hard to tell. Might be a little red, maybe not. Or we're zipping down to the Dumbbell Nebula right now. Okay. Dumbbell Nebula has definitely got some dome interference going on here. I can see it, but I'll move it just to give us that one last thing. We're looking at, this is just a beautiful object when it shows up. Let's see if I can just do 25 seconds at 1,000 and we'll see it right about here. It'll also have some red to it because, of course, the dome is in the way. Actually, be reddish blue now. So it might be purple. Yeah. Wow. That's odd. I can't even see it. Alright. Well, let me go out and move the dome, shall I?
Go right ahead.
Alright, I'll be right back.
I had a feeling he was going to leave me again, guys. Again, I'm not sure what to say. I never know what to say. Thank you all for sticking around. I know a few people have had to duck out because it's bedtime. I know this is being broadcast all over the world, so I'm not sure what time zone everybody's in. I think a lot of people aren't too far off Mark's time zone, which is Eastern, but I do appreciate you all being here and coming to support the show, and hope you're enjoying all the images. I love the cat's eye. I don't remember seeing the blinking nebula before. Do you guys remember seeing that? That sounds, I mean, it looked absolutely gorgeous. I'm not sure why it didn't come up before. Maybe it's a summer object? I watched Midnight Run for the first time a few weeks ago. I really enjoyed that. Right from the beginning, I enjoyed it all the way through. Check that out if you haven't. I think it was out in the 70s. I can't remember the year. I know our friend Bill NY Skywatcher, he was on a mission a few weeks ago trying to get all these Starlink flyovers, and apparently he did catch one and didn't realize until a few moments into the stream, and was very excited. Someone was telling me about that not too long ago. I think maybe Lorraine, maybe? I forget. Someone was there when they caught it. Oh, maybe it was Kathy, actually. Maybe it was X-Lady. And said they didn't realize at first, and it was unbelievable. So he probably still has that stream up if you guys want to look, probably from a few weeks ago. And I'm sure it's labeled. And now that Mark's back, I will go and look for Bill's channel, YouTube channel link, and you guys can go check that out. 87, thank you, Johnny. Welcome back, Mark.
Hey there. I returned. And I am trying to just see if I can get the dumbbell to show itself. That dumbbell. I thought it was right here. Oh, there it is. Yeah, it's there. It's just that I'm looking at it through clouds, so I'm going to have to... Again, this is regular white light. So what I'll do is... Wait a minute, let me just go back for a minute. Because you all know me. My name is Mark. Just one more. D'Antonio. Okay. Okay. Now I'm just going to do just one little thing. Drop it down just a tad. And then I'm going to increase the sensitivity to about 3200 and go to 30 seconds.
And I don't see the video I was just talking about.
What video, Bill?
Yeah, I thought he caught some Starlinks going by a few weeks ago.
I thought he did. Okay.
I don't know. I see the Lyrids meteor shower 2 months ago, and the Aquarids.
Aquarids, yeah.
I think that's, yeah, a month ago.
Okay.
Huh. Weird. But go subscribe to the channel anyway. It's awesome. Thank you.
Let's go see. Yeah, no, Bill has a great channel. Bill New York Skywatcher. Keisha, what episode was that on Ancient Aliens? Because I never actually worked for Ancient Aliens, but the thing is, they wanted to have me, and they couldn't pull it together. So I'm wondering if they actually bought or licensed footage from some of the other productions I've done and put it on Ancient Aliens, because I'd like to know which one it was, because I really am curious. Wow, look at this. Wow. I'm liking this. This is really pretty. Wow. Wow, look at that. Here's the classic dumbbell. Classic dumbbell. Look at that. Now you can't just view the classic dumbbell without just... Oh, I have to do this. Okay, I've got to go to filter 2, which is the wider narrowband filter. Okay. But that means I've also got to focus something a little better. So to do that, I will go here and then do this. I should have a focus star should be right in there. Okay, we have our focus. There it is. You can see the star right in there that I'm focusing on. Let's do this. Okay. I'm just focusing on the stars here. It's hard because I'm dodging some clouds, I think. Which is why this you see this one come and go. I'm dodging a few clouds. so let's pop it down. Let's do it again. Okay, we're going to try that. All right. We're going to do 4,000 at 30 seconds. Away we go. And I left the blue and red down here. You can see the blue and red of the dome.
Yeah, I like that.
Yeah, that's kind of pretty looking, yeah. But
looks purple.
it is, yeah. It does look purple because the red and the blue have blended to purple.
Why don't we see more purple objects in the sky?
I knew you were going to ask that question.
Well, I mean...
I knew it, and I was...
I mean, if I didn't, maybe someone in the chat would have, because that's kind of the logical...
Yeah.
Because the red and blue are so distinct that you can see them quite clearly together.
They are very distinct. Look at this. Wow. You can almost see three-dimensionality here on this nebula. It's amazing.
Someone commented on that. What were we looking at?
The
I can't remember. We were looking at something earlier, and someone said it almost looked three-dimensional.
Okay.
I can't remember if it was the cat's eye or the ring nebula, maybe. I can't remember. Why have we never seen the blinking nebula before? That's
the
too amazing.
Planetary. Well, no, it's a summertime object, so.
That was my guess. I guessed that when you were away.
Oh, you did? Okay.
I did.
I totally believe you because you're making your way. Into the halls of astronomy infamy, not infamy, but fame, because you're actually learning about astronomy and absorbing through osmosis more astronomy than anyone I know has ever absorbed. You know more than you think you know.
I think people you usually meet have a pretty good basis coming into it, so
yes.
there's not like new stuff they can learn. I had no knowledge of this, so I can only go up, right? Unless I just don't ever get anything.
You do. See down here, in this dumbbell, you can look and you can see that star right there in the middle. That's also a white dwarf, guys. That's a white dwarf that's powering this one. Okay, and when we look at that star, okay. As a white dwarf, it's actually causing this entire nebula to glow. That one little star, that one remnant of a star, is causing this whole nebula to glow all the way around. So all on the outside, all on the inside, we're seeing that glow from this amazing white dwarf. Okay, obviously we're looking through clouds now. I just... this other photo I just took. Yeah. Tina Peterball, you're asking about the butterfly nebula and the ring nebula?
Yeah.
We just looked at the ring nebula earlier tonight.
I wonder if maybe she was the one that commented and that it was about the ring nebula.
Oh.
Just a guess. I can't remember who said it, unfortunately. I think it was a girl. It may have been Tina, I'm not sure. But, yeah, it looks like maybe the Butterfly Nebula is a request, if possible, and...
Yeah, the Butterfly Nebula is not going to be visible to us right now. And so we'll have to wait on that one. And we have Chuck Norris with us tonight, who's not really Chuck Norris, but it's okay. He says
is that true?
The Earth's atmosphere filters out the purple colors. Not really, Chuck. I'll tell you, what's really going on. Remember, purple is a combination of red and blue light, and when we look at sunsets, we see red light. We see the red light coming through from the sun. Why is that? Why does the sun even change color on the horizon? Why should it? And the answer goes down to the fact that the atmosphere, molecules in our atmosphere, the oxygen, diatomic oxygen, nitrogen, okay, that those compounds, those molecules in our atmosphere have the ability to do a couple of things. First, when light hits them, they can basically absorb a little bit of the light and then re-emit it. Okay, that's called scattering, and that's what happens with the nitrogen molecules in our atmosphere. The nitrogen atoms will absorb a little bit of the light and re-emit it, but they don't emit it evenly. They will selectively emit some of the blue or higher energy light from the spectrum of the sun. So all over the place it's happening. The atoms are selectively absorbing some energy of the sun and re-emitting a little bit of the blue. Okay, and they do it in every direction, and thus we see, no matter where we look in the sky during the day, a blue sky. And that's why, because we're seeing blue light being emitted by the atoms in the atmosphere. It's called scattering. In fact, it's called Rayleigh scattering, a very particular kind of scattering. But then you might say, well, wait a minute, light's going onto clouds, and the clouds reflect the light. Well, yeah, but they're doing something else. Clouds are also scattering the light, and here we have water molecules doing the work, and it's called Compton scattering. And this is a scattering whereas the nitrogen molecules and oxygen selectively scatter just the blue part of the spectrum and show you the blue sky, clouds, on the other hand, the water vapor molecules, they actually scatter all of the light. So clouds look white, the same color as the light coming in from the sun. See? So that's kind of cool. Hey, Dee B's here, and Ronald has a couple of questions, which I'll get to in a minute.
And Dee had a question as well.
Okay, cool. We'll get to that too. So that's why when the sun sets, we're looking through more air over the curve of the Earth, and we're looking through much more of that air. And as we look over through more air, you have more of a chance of that blue light to be scattered between the sun and you. And thus, you see more red light coming from the sun because many more molecules of air are between us and the sun as you go around the curve of the Earth, and it's on that horizon. And so that makes the sunlight redder because the blue light is being scattered more along that path. You don't see the sun red in the sky overhead unless there's a fire and you get a lot of particles that get in the way of the sun and do more scattering. So that's how that works. And so red light and red sky in the horizon means it's the sunset. So what do we have for questions now, Amanda?
Sorry, Dee, I'm going to skip that for a second and go to Ronald's because he wants to know why we don't see green stars. So is it going to be along the same line as the purple?
Not exactly. We've talked about this one before. We've discovered there's certain rules about how hot objects radiate their energy. And one of the laws that governs them was found by a man called Wien, W-I-E-N, and he has a particular law called Wien's Law. And it shows that when an object is hot and it's radiating energy, it radiates energy from white hot to blue hot to red hot, or to yellow hot to red hot, and it never radiates green hot. Okay, although green is in the spectrum, we never get radiated green light, so we don't see. Oh, that's better. See, the cloud was over the nebula before. We don't actually see a specific green star because stars don't radiate in that singular frequency. And again, it has to do with something called black body radiation. And black bodies, again, we have blue hot, white hot, yellow hot, red hot. So all the stars are all of those colors in there. But they're not. Nowhere in there is green, and green doesn't radiate like that. So that's why we don't have green stars. What's the next question?
Okay, back to the dumbbell.
Okay.
How do you know that that's a white dwarf? That's what Dee wants to know. She says it looks like everything else.
Because I say so. No, it's not why. It does look like it's everything else, but you know what? When we look at the spectrum of that object in there, we break apart its light and get its spectrum. It's a very specialized spectrum. We're going to see very, very high energy. Okay, it's going to be very, very blue. And we're going to also be able to detect carbon atoms and oxygen atoms almost exclusively on the surface of this white dwarf. Or this object, let's put it that way. And when we look at other objects in the sky, we notice that other things like the dumbbell have a similar central star. Carbon and oxygen, very, very hot temperatures. That was really odd. But then by studying stellar evolution, we saw that when a star that's about the size of the sun dies, it will shed its outer layers, much like this star has done. And what's left behind is the exposed core, which contracts. And that contraction that we're seeing, all right, it gets down smaller and smaller and smaller. And the theoretical models back then showed that it gets to the point where the star can no longer contract anymore. If it's below a certain mass, then its gravitational contraction gets halted by an outward pressure from the atoms themselves. And that halting of the outward pressure is what's called degeneracy pressure. It has to do with the electrons in this particular case. And it works like this. If you imagine a checkerboard with all the squares, and the rule is only one electron can be in each of those squares. And because this is so hot, we have just free electrons and free protons here. Carbon nuclei, oxygen nuclei, and electrons, right? And they're all getting crammed together as a star gets compressed. And when that happens, imagine this checkerboard. You can only have one electron per square. That's quantum mechanics, laws of quantum mechanics that we found to be true. And so you can't squeeze more than one electron into a square. So now on your whole checkerboard, okay, if you imagine a 3D checkerboard all throughout the star, okay, that whole checkerboard, those electrons now are sitting in their own turf, each square. And if another electron comes up against it, they just get pressed against each other, and they cannot be mingled with each other. They can't be crushed further. That creates a pressure outward called an electron degeneracy pressure. Big words, all it means is the checkerboard's full, we can't squish any more in. All right? And the electrons don't allow any more in. And that is what holds the white dwarf in its state and not allowing it to get crunched out of existence and even smaller. Now, if the star is more massive, then we get something else in the middle of a supernova remnant, typically. And that is, let's suppose a star is collapsing. It'll collapse right past the white dwarf stage and go down to the neutron star stage. What's that? It's a star where the checkerboard now, instead of having electrons in it, it has neutrons. So no neutrons. All those neutrons are packed into this checkerboard and they can't be crushed anymore. And that is about 1.45 solar masses up to about 2.4 solar masses. And that checkerboard is now going to be just filled with neutrons, and you can't crush those anymore. That, as you might have guessed, isn't electron degeneracy pressure. It's neutron degeneracy pressure. Correct. Neutron degeneracy pressure. I heard you saying it out there. I heard that. And neutron degeneracy pressure can hold the star up as well. Now, the surface of a neutron star, kind of like a white dwarf, is hard as a billiard ball, which is like because they're so compressed. And 1 teaspoon of that stuff can weigh a few billion tons on our planet. A teaspoon. So that's how compressed we're talking here. Massive compression. Massive. So now what we look at is what happens beyond that. What happens beyond that, if a star is really massive, then it can collapse right through electron degeneracy pressure, right through neutron degeneracy pressure. And that was the weird thing. We didn't know what happened, years and years and years back. Then we figured out that the star collapses further to a point where it just becomes this singularity. What? Yeah, a small point. And that small point, being a singularity, is the beginnings of the world of the black hole. And I admit
I was gonna guess that.
Yeah. And
I was gonna guess that, but I thought maybe there was another process before that, but I figured that would be the end result.
Well, you'd be right.
Yay!
Yeah, you'd be right. So, the thing is, when we lose the degeneracy pressures, we end up finding that we have a black hole. And the black hole, people say, well, it's so powerful gravitational field that not even light can escape it. But see, that's misleading. And I've told you this before. Black holes are, of course, black holes suck. Dun-dun-dun. Okay, but black holes are really have a very high gravitational field. That's true. And what they do is, when they collapse, they actually now do something else. They don't just have an intense gravitational field that affects themselves. Their gravitational field actually affects space, just like a star. Its gravitational field affects space. This is the hard part. You thought neutron stars were hard? This is hard. The gravitational field of a black hole is so strong that it actually warps space itself. Right? So, that means that if you have a particle of light, a photon of light coming towards you, okay, it's coming towards you, it's gonna literally follow the curvature of space. What's that mean? It means that, like a car on a hill, okay, the car is constrained to follow the bumps and the curves of the hill. It's going to go up and down, and it's going to follow the hill. In the same way, light is constrained to follow the hills as well, but the hills are made of the curve of space. So if space is curved, the light's going to travel in a curve. And when you get near the black hole and you go past a certain point called the event horizon on a black hole, that's the point beyond which not even light can find a path out. It just continues to circle around inside the black hole forever. Or until the black hole vaporizes. That's to say, evaporates. Because black holes do evaporate. If in the absence of any more mass falling into them, they will evaporate. They will evaporate.
I didn't know that.
Yeah. Black holes can evaporate. They just... micro black holes evaporate very quickly, the little tiny ones that are theorized to exist. But bigger black holes, like the supermassive black hole in our galaxy, yeah, that's not going to evaporate anytime soon. It's way too big. So there you go. That's some of stellar physics for tonight. There'll be a test Monday. No, I'm just kidding. But that's I just really think that's part of the whole thing when you're trying to understand, like, these planetary nebulae. Okay, these nebulae, these are beautiful. These planetary nebulae are stunning. Okay, but you try to understand those, you got to understand what a white dwarf is. Then to go beyond, like the supernova remnants, you got to try and say, okay, well, where's the neutron star? The neutron star is in there, okay, and sometimes they spin so fast, they're vibrating in making of the supernova. These inside the supernova, the leftover inside is so has so much energy that was given to it by this rebounding pressure of the supernova, boom, that blows the star up, that it spins really, really rapidly. And sometimes it has hot spots on its surface, and that spin so that act like lighthouse beacons to light up and spin around. And we see some of those lighthouse beacons. One of them is in the Crab Nebula, and the Crab Nebula beacon comes all the way to us, and we can actually see it. And it goes like an incredible amount of times around in a second. I think it's like 30 times a second. And if you think that's a lot for a star the size of, say, Manhattan Island to spin, well, then you haven't even seen the record yet. The record is over 700 times a second that some of these stars are spinning. Okay, the remnants, yes, and those are called pulsars. Tina, you're on fire, Tina. Nice. That's a pulsar. That's right. And when the pulsar is emitting this beacon like that, these pulsars can, they could spew some really dangerous radiation at us if we were anywhere near them. But luckily, we're not. Again, we might be seeing the death of a civilization when we look at things like the Crab pulsar. We might be seeing the end. But I wouldn't count on it. I think that they would have long since figured out a way to get out of there. So, another dimension, Amanda?
Oh, yeah, we were wondering what could be on the other side of a black hole. I wasn't sure if it was like a joke, like a setup for a joke and we're trying to get funny punchlines, or if it was like just a question for chat, or...
No.
If you had to guess, what do you think's on the other side of a black hole?
Well, first of all, we have to think there's another side of a black hole. And there could be a complementary white hole. There's been some work to indicate maybe a white hole is the opposite counterpart of a black hole. And I've told you guys this before. I think if you saw the movie Interstellar, Interstellar was based on some actual physics when they actually tried to do that's beautiful. They tried to do the black hole rendering, and that's stunning. And so when they did the black hole, the consultant, the guy that helped them, was astrophysicist, Kip Thorne. And I got to sit with Kip for a while, about 3 hours, and he talked about the black hole, white hole controversy, because he had figured out that if you had a ship, you could be in a certain position, and you could actually see information about your ship coming out of the white hole before you actually entered the black hole. That's kind of like time travel, isn't it? Kind of like seeing into the future. And he sent that argument to Stephen Hawking, and Hawking told him initially when they talked about it, I don't believe that's possible. And so Thorne sent him his argument, and Hawking said, well, I'll show you, and he wrote him back an argument in return. And then they each got each other's article about this, and Thorne looked at Stephen Hawking's argument and said, oh, you know what, Stephen, you're right, it can't work. And Hawking looked at Kip Thorne's article and said, actually, Kip, you're right, it does work. So in other words, even the greatest minds on our planet can shift their ways of thinking. Kip Thorne, definitely one of the greatest minds. And Stephen Hawking definitely was one of the greatest minds. Probably unparalleled since Einstein's day. no longer with us, unfortunately. So,
that's the signs of an intelligent person, keeping an open mind, looking at other alternatives.
You're absolutely right. You're absolutely right. And you know, and so that must mean you're a genius, because you're always looking at alternatives.
Wow. I don't know about that, but thank you.
Okay. It's not a problem. Oh boy. Yeah, we got some clouds. Alright, well, you know what, guys? Always good to end on a good note. The dumbbell here, I mean, it looks purple all throughout because we're looking at it through some light clouds. I gotta say, though, they're rather compliant light clouds. It actually doesn't look that bad. But I can tell you that it could be so much better. But I have to say, tomorrow, if it's clear, maybe we'll do this again. But I am going to start taking down the telescope here. Probably not in the next week or so, but after that, and get it ready for shipping out to Arizona. I do a final confirmation that they're all set to take me out there, and I did that yesterday, and things look good out there for me to come out. And so we will do a nice job, and we'll have SkyTour LiveStream West up and running before the end of this month. Before the end of July, sorry. That's the goal. All right. So you guys, you have a good night. I will be here, well, on and off for a couple more weeks, several more weeks, and then I'll be in Arizona doing the build. But we'll have streams between now and then. It'll be fine. So you guys have a good night. Amanda, say goodbye to all your friends.
Goodbye, all my friends.
Yeah. She's great.
Be well, be safe.
Yeah, be well.
Hope to see you again soon.
Yeah.
We'll
see you all soon. And if Daryl was still here, he would have said good night, everybody. It's his favorite line. Good night, everybody. That's from Daryl. Anyway, you guys have a good night, and we will talk soon.